So today I want to talk about the possibility to automate the coding of details, verifiable details with machine learning. And the starting point is that I think we have all struggled with how time consuming it is to code for details in our studies, and how this is getting in the way of publishing more research or more quickly. So really, as a side comment, I have an engineering background, so I have always been interested in how we can automate that. But then more recently, we have been working a lot with insurers. And just to give you the context of why we want to do this even more, is that if you take a typical insurer, the kind of ones we're talking to, what they tell us, and this is real data, is that they receive about 1 million claims per year. And they estimate that about 50,000 of those are fraudulent. Now, they typically, in big companies, have anti-fraud agents, a team of 5 anti-fraud agents that check about 5,000 claims per year only. And how do they do that? Well, it could be because they had the intuition that it was fraudulent, or it could be also because it's just because of the amount, the value of the claims. But in any case, they are capped to 5,000-ish claims to check. Out of those, they are able only to prove as fraudulent and not reimburse only 500 typically of those, all the other claims being reimbursed. So we see that the conversion rate is very, very low. And so we have an interest in trying to have the 5,000 claims checked as relevant as possible, and in an ideal world, have all of them being fraudulent. So this was the starting point, and for this we need, of course, to get some automation to analyze the claims, especially in terms of the details and verifiable details. So what was the technology we used as the basis of the study? Well, we use a technology called Hexagon, and full disclosure, this is a startup company I have created 3 years ago. So I'm involved in this, but I just want to show you how it works and how it was the basis for this project. So just playing a video very quickly.
This is disgusting.
Okay, so here you can see that I was smiling. So in the facial tab, it's detected as joy. In the vocal tab, you can see that it was also detected as joy in the voice. But then in the transcript, it was detected as disgust, of course, because of the word disgusting. And then we fuse all of this in a multimodal tab. So this is just to say that so far the technology was only focused on emotion, but now we use this technological basis to expand on detail coding. So what data did we use? We had only French data so far, 2 data sets. A first data set with 240 statements that were coded for total details and verifiable details, about 10,000 total details and about 1,000 being verifiable. Importantly, this study, this was from a former study where participants performed a mock crime or not, and we collected their statements orally and then transcribed those for the study. Whereas data set 2 was totally different, because this one, it's a small data set, it's only 80 statements, but it was in an insurance claim setting where participants provided written statements right away. So 2 different data sets, and because of the differences in their sizes, we have used data set number 1 to perform the training of a machine learning model with 80% of the data, and 20% used as a test set number 1. And dataset 2, given it was a small dataset, was entirely used as a second test set. The coding of the details was done in the traditional way, manually. So for each word, we coded if they were spatial, temporal, or perceptual detail, and then for each of those details, whether they were verifiable or not. So this is in French, so I'm just going to translate the first line. But for example, here we can see that the first line, quand je suis arrivé, meaning when I arrived, was coded as a temporal detail. Okay, so what are the challenges? What were the challenges now of using a machine learning approach to such a project? Well, first, there's the question of how you represent the text for machine learning purposes. And second, and more importantly, you have some unbalanced classes here. So for example, in our first data sets, the proportion of verifiable details was only 12% of the total details. So it's not balanced, it's really unbalanced, and we have to deal with this. So what was our approach? Well, first, we converted text into embeddings, vectors in machine learning terms. So here we compared 4 text representation options. Second, we used a custom entity recognition model to detect the details as spatial, temporal, or perceptual. And then to compensate for the classes that were unbalanced, we used methods of oversampling. And last, we used a binary classifier for each detail to predict whether the detail was verifiable or not. And this time we compared 11 different classifiers, which I won't go into the details here, but just to show that we tested different approaches. Just a word on the oversampling method we use. So we didn't use the traditional method consisting in just duplicating the data because this doesn't bring any new information for the model to learn. But we use another method called the SMOT method, which consists in the vectorial space to select here in red an example of the minority class vector. And then we look at the nearest neighbors of the same class, the minority class, and then we randomly generate. So we draw a line between 2 minority class samples, and we generate a vector randomly along this line. So this brings more information for the model to learn. Okay, so what about the results on test set 1? So we get an AUC of 0.78, or alternatively an accuracy of 85%. So this seems pretty good, but of course an accuracy rate is not really relevant when the classes are unbalanced, or how can I say that? All accuracy rates are not made equal, right? Because if you build a trivial model, always predicting that all details are non-verifiable, because of the class, how they are unbalanced, you would get an 87% accuracy rate, and yet the model would be useless. But here we can see that it's still interesting because we get, I think, a pretty decent recall of 0.61 on the verifiable details and a precision of 0.41. And this compared, for example, to a random prediction is, for example, in terms of recall, 3.5 times more performant than just a random prediction. So I think those are very promising results. Now, I want to say that it's really a message of hope that I think we can really get there. And we are really very close because the data set was really small, and yet the performance are, I think, quite promising. Now, it doesn't mean that we don't have a lot of challenges to overcome, because on test set 2, the one that was used entirely as a test set, the AUC dropped to 0.52. So, so this was a little disappointing, but I think it can easily be explained because the data set has not been used at all, of course, in the training, but this should be no excuse. It's mostly that the contexts were so different. In one case, we had insurance claims, in the other mock crime, so the context is very different. And second, and most importantly, I think the tone was very different because we had some written statements in the test set 2, whereas in the first one, it was oral statements. So I think it's mostly a matter of training the model in the relevant context. This is just to show you that then, of course, you can automatically have some coding of the details and also of the verifiable details. So just to conclude, what's the next steps? Of course, is to improve the performance and the robustness of the model further. And how can we do that? Well, of course, with training with more data, as always in machine learning projects. Second, in more context, meaning like having like insurance claims context, crime context, etc., so that the model becomes either more robust or that we have the ability to build one model per use case. And last, of course, with more languages, because here it was only trained in French. Thank you very much.